We often think of steel as the ultimate symbol of permanence, a material that defines the strength of our modern world. We build our cities and our bridges with it because it generally behaves in a predictable way, bending and stretching before it ever reaches a point of total failure. But there are moments in engineering history where the very strength we rely on becomes a hidden vulnerability, and few cases illustrate this more clearly than the story of the Silver Bridge. Built in 1928 to connect Point Pleasant, West Virginia, to Canoga, Ohio, this structure was a marvel of its time, utilizing a specific design known as an Eyebar suspension bridge. Unlike the graceful cables we see on bridges like the Golden Gate, which are composed of thousands of individual wires, the Silver Bridge relied on high-strength steel links called eyebars. Imagine a massive steel bar, several inches thick, with a circular hole at each end. These were pinned together to form long, heavy chains that draped over the towers to support the roadway. At the time, this was considered a triumph of efficiency. By using a new type of heat-treated carbon steel, engineers could create a bridge that was lighter and more economical than traditional designs. However, this efficiency came with a trade-off that was not fully understood in the 1920s. The material was incredibly strong, but it lacked a property we now call fracture toughness. It was strong, yes, but it was also brittle. In the world of structural engineering, the Silver Bridge was what we call a non-redundant structure. This means that there were no backup systems. The entire tension of the bridge was carried by just two eye bars running side by side in a chain. If one failed, the other was never intended to carry the weight alone. For nearly 40 years, the bridge served its purpose, standing silently over the Ohio River. But beneath the surface, at the microscopic level, a quiet and invisible process was taking place. The evidence points toward a phenomenon known as stress corrosion cracking combined with corrosion fatigue. To understand this, we have to look at the joint where the eye bars were connected by large steel pins. Inside the hole of one specific eye bar, labeled Eyebar 330, a tiny crack began to form. This wasn't caused by a sudden impact or an obvious defect, but by the confluence of three specific factors: a susceptible material, constant tension, and a corrosive environment. The high-strength steel was the host. The weight of the bridge and the vehicles crossing it provided the stress, and the moisture of the river valley, perhaps mixed with pollutants, provided the chemistry. In this hidden corner of the assembly, where inspectors could not see, without completely dismantling the joint, the crack grew with agonizing slowness. It started as a microscopic pit, a small blemish on the inner surface of the steel. Over the decades, every time a car or a heavy truck rolled across the deck, the stress at the tip of that tiny crack would spike. This is the mechanism of corrosion fatigue, where the environmental damage and the mechanical loading work together to pull the atoms of the steel apart, one by one. By 1967, the crack had grown to a length of only about 0.1 inches. In a more ductile material, a crack of that size might have been harmless, simply causing the metal to deform slightly. But in this specific heat-treated steel, that tenth of an inch was the tipping point. The common view of structural failure often involves a slow, visible warning, but the physics here were different. Once the crack reached its critical size, the steel could no longer contain the energy stored within it. The fracture didn't creep, it accelerated at the speed of sound. The eye bar didn't bend, it shattered like glass. This single point of failure in the chain assembly meant that the load was instantly transferred to the lone remaining eye bar in that link. Under the sudden, violent shift in weight, the second bar twisted and slipped off the pin. Without that chain to hold it up, the equilibrium of the entire bridge was lost. The towers, no longer balanced by the tension of the chains, were pulled over by the weight of the remaining spans. The entire event took less than a minute. In the aftermath, the forensic investigation changed the way we look at infrastructure. We realized that high-strength materials require even higher levels of scrutiny. We learned that redundancy isn't just a luxury, it is a necessity for public safety. This led to the creation of the National Bridge Inspection Standards, ensuring that every bridge in the country is regularly evaluated for the very types of hidden flaws that claim the Silver Bridge. It was a hard-learned lesson in the behavior of materials and the importance of understanding the microscopic world when building on a macroscopic scale. The evidence reminds us that the integrity of our largest structures often rests on the smallest details, hidden away in the dark corners of a joint. If you find these explorations of the invisible forces that shape our world valuable, I invite you to follow along as we continue to look closer at the engineering that holds our lives together. Thank you for listening.